So let's talk about this stuff. So let's start off with an introduction to expected value, variance, and standard deviation. You might like to see that. Okay. And just right from the get-go, I should point out expected value has a lot of different names, right? Another name for expected value is the mean or the average. So those are all three names for the same thing. So expected value, average is just what you think it is. So I'll start off with an example. Let's find the average or expected value of the following test scores. Zero, 0, 100, 100, 80, 20. Hopefully these are not the test scores in anyone's class, right? People didn't take the test. Okay, so a couple symbols for mean, X bar or mu are both symbols we use, or capital E of X. Those are all valid symbols. And if you take a stats class, you'll learn more about kind of the difference in meaning between these. Like, for example, just to kind of point out, X bar is usually like your sample mean, meaning if you're taking a sample from a larger population, we call it X bar, whereas mu is the actual mean of the entire population. So not that that's important here really, but if you do take a stats class, it is worth knowing the difference between what these symbols mean. Neat. So this is going to be 0 plus 0 plus 100 plus 100 plus 80 plus 20 divided by the number of observations, which is 1, 2, 3, 4, 5, 6. And that adds up to 300 over 6, which is an average of 50. So the mean is just a measure of the middle. There are other measures of the middle as well, but this is the one we look at often. And then let's welcome, come on in. Morning. Thanks. There are lots of ways of calculating this. You could, right, usually when you do an average, you add them all up, divide by the number. You could also think of each individual score being divided by the number of scores, right? It's the same thing. You could also think of it as each individual score, and this is kind of the more important way of thinking of it, each individual score multiplied by the probability of seeing that score. So looking at these scores, right, there's a 1/6 probability of seeing that score, there's a 1/6 probability of seeing that score, and so on. There's a 1/6 probability of getting 100, there's another 1/6 probability of getting 100. I should probably put those together. There's an 80 times a 1/6, and there's a 20 times a 1/6. So what I would actually write is this is 0 times 2/6 plus 100 times 2/6 plus 80 times 1/6 plus 20 times 1/6. And so the reason we kind of think about it this way is because a lot of the times not each event or each score is equally probable. So when we're calculating an expected value, the more kind of general way of calculating it is to take each value and multiply it by the probability of seeing that value. So when we're talking about expected value, the kind of usual way of calculating is taking each score and multiplying it by its probability. So a score of x1 times the probability of x1 plus a score of x2 times the probability of x2 plus a score of x3 times the probability of x3 plus a score of x4 times the probability of x4. That's what each of these is corresponding to. So our first score, our x1 is 0, and our probability of x1 is 2/6. Our second score is 100, and the probability of seeing 100 is 2/6. Our third score is 80. The probability of that is 1/6. And our fourth score is 20, and the probability of that is also 1/6. More, right? Question? Sorry.
No, I thought it was Thursday.
Today's Tuesday. Today's Tuesday, May 24th. Generally, right? The expected value of x1 through xn is given by e of x equal to x1 times p of x1 plus x2 times p of x2 plus all the way to xn times the probability of xn, which is often condensed using sigma notation as the sum from I equals 1 to n of x sub I times p of x sub I. Cool. And then we're going to also talk about the standard deviation and the variance. So we'll talk about variance first. So the variance of these scores, we typically use the symbol v of x. And the way we calculate it is, so variance is a measure of how much something is varying. So we want to know, kind of compared to the mean, which was 50 for the last example, how much do our actual scores differ from that mean? This is one way of measuring it. It's not the only way of measuring how things differ from the mean, but it's kind of our most often used one. So the variance is going to be, take each score, subtract the mean. So I'm going to get 0 minus 50. That's one of my scores. And then square it. And then multiply by the probability of that score. All right, so I took my score of 0, that right, my 0 was my x1, and there's my probability of x1. And there's the mean, x bar. Why are we squaring it? The reason we're squaring it is because we want all the things to be positive. Right? If we didn't square it, 0 minus 50 would definitely be negative. So that's why we're doing the squaring, to kind of get a measure that is positive. Otherwise, if we didn't square it, you kind of have all these things kind of canceling each other out. You get some negative ones, some positive ones, and it wouldn't really be as meaningful. So then we're going to do that with the rest of the score. So we're going to take our x2, which was 100, minus the mean, squared, times the probability of that, which was also 2/6. So again, right, that's my x2, again, my mean, and there's my probability of x2. And then we had, what was the next one? 80 minus 50 squared times 1/6, my x3, my probability of x3, and finally 20 minus 50 squared times 1/6. Yeah, that's my fourth observation, and there's the probability of that observation. Adding this all together, let's see what we get. So 50 squared is 2,500. So I'm going to get 2,500 times 2/6 plus another 2,500 times 2/6. 80 minus 50 is 30. 30 squared is 900. So 900 times 1/6 plus also 900 times 1/6. And putting that all together, we get approximately 1,967. Okay, that doesn't feel super meaningful, right? Like, it's this giant number. The average was 50, and the scores were from 0 to 100. The variance is kind of a bizarre measure of things. So what we do with the variance is we take the square root of it to undo that squaring in some sense. So the standard deviation is just the square root of the variance. So people often talk about calculating the variance because it's the more general thing, but then we always find the standard deviation from it. So if I was a professor teaching in class, I would focus more on how you calculate variance, because after you know how to calculate variance, standard deviations literally just take the square root. So here the standard deviation is going to be sigma equal to the square root of the variance, which is the square root of 1,967, which is approximately 44.3. And that, for our bizarre set of test scores, right? So 44.3 is the standard deviation of the 6 test scores. 0, 0, 100, 100, 20, and 80. That seems not unreasonable, right? If you had bizarre test scores like that, the standard deviation would be 44-ish. That's in the realm of reasonability. And normally, when you have like actual test scores distributed in the class, there's like a couple hundred people at least, and you have like a mean that's maybe around 70, and your standard deviation is probably a bit smaller because you have a lot more test scores that are closer to the middle. So that's kind of a more realistic idea of what's going on. On the other hand, just as a counterpoint, if you gave a test and all 6 people in the class scored 50, first of all, you might wonder what's going on. It'd be weird that everyone got the exact same score. If everyone got the same score, well, definitely the average is 50, right? There's no doubt about it. The mean is 50. Add those all together, divide by 6, you're going to get 50. And the standard, well, I should say, and the variance is going to be 0. Right? There is no variance from the mean. Everyone literally got the same score. There is no deviation whatsoever. We could also calculate it. Right? If we calculate the variance here, it feels kind of silly, but it's going to be your score minus the mean squared times the probability of getting that score, which is 6 out of 6. Well, that's a big old 0. So you don't often see things distributed with a mean or with all the same score with a variance of 0, but it can happen. Also, the standard deviation would be 0. Not very exciting, but just point out. So generally, the variance is calculated as each score minus the mean squared times the probability of that score. So x1 minus mu squared times the probability of x1 plus x2 minus the mean squared times the probability of x2 plus all the way to the last score, xn minus the mean squared times the probability of xn, which we then could write also using sigma notation as the sum from I equals 1 to n of x sub I minus the mean quantity squared times the probability of x sub I. And then the standard deviation is just the square root of that. I should mention, so far, these are all formulas that are meant for discrete distributions, right? Where you have a finite number of or I should say a countable number of observations, where you can just say, oh yeah, each thing multiply the probability. That's going to be a little bit different, although similar to a continuous distribution, which we'll get to a little bit later. But like, so when you think of discrete versus continuous, my go-to example in my head is always like shoe size versus the length of your foot. Shoe size is a discrete variable, right? You can, using the American system or whatever, you can be like an integer or a half size, right? 6, 6.5, 7, 7.5, right? So on and so on and so on. There's only a finite number of possible shoe sizes. Whereas if someone was measuring the length of your foot, there are literally an infinite number of possibilities because you can keep measuring to a finer and finer gradation. So someone could have a foot, that was 6 inches long, or 6.1, or 6.2, or 6.35, or right, you could get finer and finer and finer. So you could certainly discretize it, right? Make it discrete by saying, well, we're going to limit it to like the first 10th of a decimal place. And then you would say there's only a finite number of possibilities. But technically, there's an infinite number of possible foot lengths. So that's kind of the difference between discrete and continuous. Continuous, you get kind of any value in a range, whereas discrete, we're limiting the number of values to this or this or this. And even if my foot is, 8 inches long and your foot is 8.1 inches long, we both wear a size 11 or whatever. That's kind of the idea. So let's talk more about discrete probability. And this is section 9.1. Discrete. Finite number of possibilities. Another good example, just to kind of counterpoint, of continuous example is like how long it takes for a bus to arrive is often an example given in textbooks, because the amount of time can literally be any amount of time between 0 minutes and 15 minutes, for example, right? It could be, there's an infinite number of possible times you can wait between those two endpoints. Well, let's look at this discrete example. The coin is tossed 4 times. Let x equal number of heads that come up. So first, we're going to list the sample space. So the sample space, sometimes people use the symbol omega for it, although that's more of probably, yeah, it comes up in different classes. Sometimes people call this omega. The sample space is literally the set of all possible things that can happen. So one thing that could happen is when you get 0 heads, I could flip tails, then tails, then tails, then tails. Right, that's one possible thing in my sample space. That's one event that can happen. But I could also get 1 head. Now there's more than one way of getting 1 head. Maybe I flip the first coin ahead and the next 3 tails. Or maybe the first one's tails, the next one's heads, and then tails and tails. Or maybe it's tails, tails, then I get a heads, then I get a tails. Or maybe it's tails, 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 then a heads. Or we could get 2 heads. I think you see where this is going. I could do heads, heads, tails, tails, or heads, tails, tails, heads, or heads, tails, heads, tails, or that's all the way heads can be first. So then I have a tails, heads, heads, tails, tails, heads, tails, heads, or tails, tails, heads, heads. And those are all the ways you can get 2 heads. I want to get 3 heads. It can be heads, 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 tails, heads, heads, tails, heads, heads, tails, heads, heads, or tails, heads, heads, heads. And finally, if I want to get all 4 heads, there's going to be heads, 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 heads. I might have started off, if I'd been thinking about it, with how many possible things that can happen. Well, when I flip the first coin, or when I flip the coin the first time, there's 2 possibilities, heads or tails. And then when I flip the coin the next time, there's 2 possibilities, heads or tails. Then I flip the coin the next time, there's 2 possibilities, heads or tails for each of those. So you kind of think about a branching little tree where in the first branch I get heads or tails. And in the next branch I get heads or tails. In the next branch I get heads or tails. And the next branch I get heads or tails. So there's a lot of branches here. There's going to be 16 possibilities, right? Because there's 2 choices times 2 choices times 2 choices times 2 choices. So the total number of possible outcomes is 2 to the 4th, which is 16. And each of those are equally likely, right? Each one of these 16 things I've written down here has an equally likely chance of happening. Are there 16 things there? Let's see. There's 1 here, there's 4 here, there's 6 here, there's 4 here, there's 1 here. 1 plus 4 plus 6 plus 4 plus 1, yeah, that's 16. So there's definitely 16 possibilities, and each one of them is equally likely. So let's go ahead and write the table for our variable x. So oftentimes you'll see a table like this, where you have in the first row the values x can take on. So in this case, the values of x are 0, 1, 2, 3, and 4. And then below that, the probabilities of those values. So what's the probability of flipping 0 heads? Right, 1 over 16. And in general, we don't talk about this as much in math, but the probability of something happening is the number of ways it can happen divided by the total number of possible outcomes, which is exactly what you already inferred. But if we're trying to make it more formal, that's the way we say it, right? Number of ways of getting what you want divided by the number of things that can happen. And then the number of ways of getting flipping 1 head would be 4 out of 16, which we could reduce to 1/4. The number of ways of getting 2 heads, or the probability of getting 2 heads, is 6 out of 16. The probability of 3 heads is 4 out of 16. And the probability of 4 heads is 1 out of 16. Couple things to notice here, and this is always true. Thing 1, the probability of x for any x is always between 0 and 1. I suppose if you look back at our previous example of all 6 test scores being 50, the probability of someone scoring a 50 on that one was exactly 100%, or 1, because each test score was 50. The other thing, which is useful, is that the sum of the probabilities have to add up to 1. So if we add up the probability of x equal to 0 plus the probability of x equal to 1 plus the probability of x equal to 2 plus the probability of x equal to 3 plus the probability of x equal to 4, that has to add up to 100% or 1. Because if you take all the things that can happen, that's all the probabilities have to add up to 100%. Because if I say, well, what's the probability that someone scored a 0 or flipped 0 heads, 1 head, 2 head, 3 heads, or 4 heads? It'd be like, well, 100%. One of those things had to have happened. There is no other option. But then we can use this table to answer other questions like, what is the probability of flipping at least one head when tossing 4 coins? Well, we can literally look at the chart and see what those probabilities are. So the probability of tossing at least one head. So the probability, it is good to take the question they've asked you and rewrite it in terms of your variables that you've used and kind of the notation. So probability of flipping at least one head, I'm going to write as the probability that x, the number of heads, is greater than or equal to 1. And that's how I would write it using the notation I have decided on. And then that's going to equal the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. And I'm just going to add those up. That's going to be 4/16 plus 6/16 plus 4/16 plus 1/16, which is going to be 15/16. Now, I've certainly done this question kind of the longer way. A shorter way would have said, well, the probability of flipping at least one head is 100% minus the probability of flipping no heads. So I could have said, or it's going to be 1 minus the probability of flipping exactly 0 heads. That's the only thing that can happen that isn't flipping at least one head. And that's going to be 1 minus 1/16, which is also 15/16. Which really, this is just using the idea, right, that everything has to add up to 1. So if I know that probability of 0 heads plus 1 head plus 2 head plus 3 head plus 4 head adds up to 1, or 100%, well, if I want this, then I can do 1 minus the other stuff. Really what this is, it's the idea of called with the complement. If you're trying to find the probability of some event, let's just say A, it's equal to 1 minus the probability of not A. The notation for that is typically a complement like that. And again, that's probably more of a stats notation than you might see in this class, but it doesn't seem like it's bad to mention. This just means everything that is not in A. This is everything in A. So in this particular example, A was the event that the number of heads was greater than or equal to 1, and not A was that the number of heads was strictly less than 1, which meant that the number of heads was exactly equal to 0. That's the idea there between these two things. We can, of course, calculate the expected value of x. Now, let me ask you all 2 of you and 3 of you on Zoom. If I were to flip 4 coins, what would I expect? How many heads would I probably expect to get if it's a fair coin? Right, 1/2 the time, which would be 2 heads. So I'm going to expect 2 heads, and that is generally true. Your expected value for these discrete probabilities, if you've got something like this that's fair, is going to be the probability of getting a head, which is 1/2, times the number of times you do it, which is 4. Totally works. So the expected value of the number of heads is going to be, well, I'm just going to take my previous table and do some multiplication. It's going to be 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16. That's going to be 0. Okay, 0. That's going to be 4/16 plus 12/16 plus 12/16 plus 4/16. That's 16/16, which is 1, plus another 16/16, which is indeed 2. Just like we expected. Really, nothing. Expected value. We expect that. I know. So then let's talk about the variance. Variance, again, is a little more work to calculate. The variance is going to be each observation minus the mean squared times the probability of that observation. So notably, you have to calculate the mean or the expected value before you can start calculating the variance. You have to have that before you do the other one. In this particular case, again, just looking back at my table, and now knowing that the mean is what it is, my variance here is going to be 0 minus 2 squared times 1/16 plus 1 minus 2 squared times 4/16 plus 2 minus, I don't even need to write this one, but I'm going to, right? I shouldn't write that one really though, because I know that's going to be 0, because 2 minus 2 is 0, plus 3 minus 2 squared times 4/16 plus 4 minus 2 squared times 1/16. To calculate this, let's see, 0 minus 2 squared is 4, 4 times 1/16 is 4/16. That's going to be 1 times 4/16, 0, 1 times 4/16. I think all of these terms end up being 4/16, which is kind of funny. So you get a 1. So our variance is 1. Okay, that seems reasonable. And if I flip 4 coins, I expect to get 2, but I'm not always going to get 2. My variance is 1, meaning, right, a lot of the time I'm going to get 1 or 3, and maybe occasionally I'll get all 4 heads or all 4 tails. Or I should say 0 heads or 4 heads is what I should really say, some type of number of heads. And then, of course, the standard deviation would just be the square root of the variance, which will also be 1. How exciting. Talk about that formula here. No, not really. Yeah, it kind of seems maybe worth mentioning at this moment. No, we'll come back to it. So I will mention there is an alternative formula for variance, which we'll come back to when we start talking about continuous, which we are going to get to today. Well, let's look at another example. Suppose the game is designed so that a player receives $5 for flipping 3 heads or 3 tails, but loses $2 for any other combination of 3 coins. Is this game fair? Well, fair is not really a great label. Fair to who? Right? The person who's running the game or the person who's playing the game? So to be more specific, when we ask if a game is fair, what we really mean is the expected value of the winnings $0? A fair game is when you expect to win $0 over time. Not the kind of game I really want to play because it feels like a waste of time, but there's other aspects to playing games. Like it just be fun, it could be exciting. So I want to find the expected value. Why? Actually, before I even say, so I was about to say I want to find the expected value of X, but what is X? So let's call X the amount of money won. Okay. So I could win $5. What's the probability of winning $5? Well, I'm flipping 3 coins. So there's 8 possibilities, 2 times 2 times 2, and only 2 of them are winners for me, right? Either tails, 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 or heads, heads, heads. But any of the combinations with one tail and two heads, or one head and two tails, right, all of these are where I lose money. So what's my probability of winning $5 if I play this game? Looks like,
Yeah.
say that one more time?
Yeah.
Not quite. So actually I want to speak to the probability couldn't be 3 halves because that number is bigger than 1. So the probability has to be a number that's between 0 and 1. So how many ways are there that I win? 2 out of how many total possibilities? 8. So our probability here is going to be 2 out of 8 of winning.
Do you have the expected value?
I don't know. That's actually what we're going to find. It might be. I'm not sure. Let's see. So then, what about? So I've described X as the amount of money I'm going to win. So X could be $5 if I win, but if I lose, I shouldn't say it's $2. I should say I'm going to win -$2. So if you're talking about X being the amount of money you're winning, and you're winning or losing money, the amount you win should be positive. The amount you lose should be counting as negative winnings. And then the probability of that happening is going to be 6/8. Because there's 6 ways out of 8 total ways I can lose. So then my expected value of winning, the expected amount, the amount of money I'm going to expect to win is going to be $5 times, I'm going to reduce this fraction to 1/4 plus -$2 times 3/4. Let's see, that's going to be 5/4 minus 6/4. That's going to be -1/4 or -0.25. So I expect to win -25 cents. So I mean, that means I expect to lose 25 cents. So the game is not fair. And more importantly, it's not fair, not in my favor. So the game is not fair. And it is not unfair in my favor. Right, so I should just point out, if things were the other way around and the expected value ended up being like positive 50 cents, I still wouldn't say that the game is fair. I would play it because I'm going to win money, not a lot, but it's not a fair game, because a fair game is one where your expected value of winning is $0.
But it also would be fair for you.
Right, exactly. Specifically, it wouldn't be a good idea to play this game, because over time you would expect to lose 25 cents every time you play it. Right? Occasionally you're going to win $5, but more often than not, you're going to lose $2. And so if you played this game, 1,000 times, you would expect to lose on average 25 cents every time you played it. And 25 cents times 1,000 times is going to be $25. So if you play this 1,000 times, you would expect to have lost $25. Interesting. Because each, right, this expected value here is how much you expect to lose each time you play. Right? You can't actually lose 25 cents when you play it. Right? You're either going to win $5 or you're going to lose $2. But if you play it enough times, you're going to see that over time, on average, you will have lost 25 cents for each time you have played. So if you play it 1,000 times, you're going to lose approximately $1,000 times 25 cents, which is $25. That's the idea with this expected value, right? The expected value sometimes isn't meaningful. Just as another example of this, a really quick one. If you roll a 6-sided die, well, each possible side has the same probability. So if X is the number showing, then our table, and it's good to be able to complete these tables. Our values of X are 1, 2, 3, 4, 5, or 6, and the probabilities are each 1/6. If you ever have to complete these tables, the things to remember are: 1, all the probabilities have to be greater than or equal to 0. Usually they're not 0, because if they were 0, you wouldn't include them. And 2, all the probabilities have to add up to 1. So if I want to find the expected value of my die roll, it's going to be 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. And if I add that up, 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. So it ends up being 21/6, which reduces to 7/2, which is 3.5. So your expected value of a die roll is 3.5, but you can't actually roll a 3.5, right? I'm either rolling a 1, 2, 3, 4, 5, or 6, but you would see that over time, if you roll the die, say like 10 times and added it all up, you would expect that, okay, if I roll it 10 times, the sum of the rolls are going to be close to 35, because it's going to be your expected value of 3.5 times how many times you rolled it, which was 10. Do it sometimes. If you got right, you get all 10 times, right? If you're bored, roll some dice, record how many things you get, see what over time, like if you roll a die like 100 times, you should get a total of close to 350. Not exactly, right? Because it's not exact, but it'll be close. Do one more example of discrete, and then we'll start talking about continuous. Because continuous is really where it's at for this class. But it's good to see the discrete stuff first. Yeah, sure. I didn't number the other ones, but I just numbered this one for some reason. Insurance. So insurance claims and their probabilities are shown in the table below. What annual premium should the insurance company charge so that they break even? So here's our table. So X is going to be the dollar amount of the claim, and P of X is the probability that that dollar amount claim happens. So we can have a $0 claim, we can have $1,000 claim, we have a $5,000 claim, a $10,000 claim. And the probability of making a $0 claim is 0.936. So most of the customers aren't going to make any claims. It's pretty typical for insurance. Probability of someone making a $1,000 claim is 0.040. Probability of making a $5,000 claim is 0.020, and the probability of a $10,000 claim is 0.004. And if we check, those probabilities should all add up to 1. And they do, because 0.936 plus 0.004 is 0.94, and then 0.94 plus 0.04 is 0.98, plus 0.02 is 1. But it's a good idea to check, because oftentimes there are definitely questions in the textbook. They'll give you like a table like this, be like, is this actually a probability distribution? And you'll be like, oh, do the probabilities add up to 1? Are all the probabilities non-negative? If those two things are true, then yes, it is. So what's the expected value of the claims we're going to have to pay as an insurance company? Well, it's going to be the usual $0 times, I really don't even need to write 0.936, plus $1,000 times 0.040, plus $5,000 times 0.020, plus $10,000 times 0.004. So that's going to end up being 0 plus 40 plus 100 plus 40, which seems like it's going to have to $180. So if we charge each customer $180, then we should break even if we expect our claims distribution to look like this. This is a very kind of basic example, but this is not unlike what people actually do as actuaries, right? Actuaries do assessment of risk, specifically assessment of risk from the company's perspective. And so they're trying to decide, okay, how much do we actually charge customers so that the company is financially solvent, but still able to cover all the claims that they actually make. And I think about this somewhat often. My wife actually works for an insurance company, so like that there are actually people that she talks to, like, who do this job. Like, oh, we need to actually figure out. Obviously, it's much more complicated math than just like, here's a table of things we think are going to happen. But that's kind of the basic gist of it, is really kind of trying to figure out what do we expect to happen and how are we going to prepare for that. It's kind of interesting. Or it's super boring, depending on your perspective. Some people are like, I mean, actuaries are supposed to have very good job satisfaction, but they always get the kind of rap of having a boringish job if you're not into that kind of thing. Okay, let's move on to continuous. So continuous probability. So let's look at some examples. Let's talk about the weight of a potato in pounds at harvest is modeled by the following probability density function, which we often abbreviate as PDF. So here's the function. F of x equals 3/14 times the square root of x, where x is between 1 and 4. So just as a point, on the very low end, a potato would weigh 3/14 times the square root of 1. So 3/14 of a pound. It's not very much, right? It's like 0.2 pounds. I mean, there's a lot, right? Potatoes vary in size, right? They're definitely very small potatoes, they're very large potatoes, lots of room in between. I like the small ones, actually, pretty good. On the high end, we could get a potato that would weigh, well, if I plug in 4 for x, 3/14 times 2 is going to be 6/14, which is 3/7. So almost half a pound. It's kind of a big potato. So something to know, when we talk about continuous distributions, instead of all the probabilities adding up to 1, well, we still have this idea of all the probabilities adding up to 1. The problem is I can't add them all up, right? X can literally be any value between 1 and 4. So I can't be like, okay, it's going to be x equal to 1 times the probability of 1 plus x equal to 1.1 times the probability, right? I can't add up all these probabilities. So instead what I'm going to do is I'm going to think of it graphically. Here's 1, here's 4, and here's my function. Looks like this. And what should be happening here is that so I made a mistake. It's not terrible, but I should definitely correct it. So these numbers are not right here. These numbers are probabilities that don't really have a meaning. So I should apologize heavily. So the weight of the potato is x. So on the low end, the potato could weigh 1 pound. On the high end, the potato could weigh 4 pounds. And then this f of x here is supposed to be the probability of getting that weight. So that's definitely a better way of saying it. Sorry. That's it. Okay. So the first thing to note here is that the area under the curve better equal 1. Just like with the discrete random variables where all the probabilities add up to 1, for a continuous random variable, all the probabilities have to add up to 1. We can check this. I don't think we really need to check it, but it should be true. It's verifiable. Yeah, I'm going to let you all do this later if you want. Verify that this area from 1 to 4 of 3/14 times the square root of x dx, that is indeed equal to 1. Okay, but I'm going to let you do that on your own. We're going to answer a different question. Question of having more root. So let's let's find the probability that a randomly selected potato weighs between 1 pound and 2¼ pounds. So when you're finding the probability for a continuous random variable, you're finding the area under the curve that correlates to those values. So graphically, here's what this is going to look like. If, again, if this is my distribution from 1 to 4, it's like this. What I'm going to try and find is the area under this curve from 1 to 2¼ So I'm looking for that area right there. So that area, which is equal to the integral from 1 to 2.25 of my function, that is equal to the probability that my potato weighs between 1 and 2.25 pounds. Or written a little bit more succinctly, the probability that x, our variable, is between 1 and 2.25 is equal to the integral from 1 to 2.25 of your probability density function. So now let's calculate it. So I'm going to do the integral. I'm going to get 3/14 times x to the 3/2 times 2/3 from 1 to, I'm going to change 2.25 to a more recognizable number. It's 9/4. Right, 2¼ is 8/4 plus 1/4 is 9/4. And then cancel some 3's, cancel a 2. You're going to get 1/7 times x to the 3/2 from 1 to 9/4. And get 1/7 times 9/4 to the 3/2 power minus 1 to the 3/2 power. 9/4 to the 3/2 is simplifiable. 9 to the 3/2 power is 3 cubed, which is 27. 4 to the 3/2 power is 2 cubed, which is 8. Just becomes 1/7 times 27/8 minus 1, which is going to be 1/7 times 19/8. Which I guess is 19/56. So that's the probability of getting a potato that weighs between 1 pound and 2¼ pounds. 1956. Which we could write as a decimal, but we should leave it as a fraction. Now, that's a good question. It's a better question if I had more room. Let's go right here. Come on, papers. What's the probability that a potato weighs more than 9/4 pound? Well, it's just the rest of the area, right? If we know the probability of a potato weighing less than 2¼ pounds and more than 1, right? Because we have to be between 1 and 4, right? I didn't say it here, but the implicit thing not being said is it's also less than 4 pounds, because all the potatoes we were talking about are between 1 and 4 pounds. If we know the probability of weighing between 1 and 9/4 is 1956, and the probability of weighing more than 9/4 is 1 minus 1956. So we could either calculate this as the probability that x is bigger than 2.25 but less than 4 as the integral from 9/4 to 4 of your 3/14 times the square root of x. And since we've already done the work, it'd be easier just to be like, oh, it's going to be 1 minus the integral we already did. which is going to be 1 minus 19 over 56, which is what? 56 minus 19 is going to be 37. So, right, if you know the area under the curve is equal to 1, and you have found this area and you want to find that area, you just subtract it from 1. That fact is going to come in handy a lot because some of these distributions we look at in section 9.3, I think, so this is special ones where you're going to be doing improper integrals. And so so in the future, there's going to be a question be like, well, what's the probability that, your variable is less than 2? And then they'd be like, okay, what's the probability that your variable is bigger than 2? And instead of doing the integral from 2 to infinity, which is not terrible, it's doable, you can be like, well, it's just going to be 1 minus the thing I already calculated. So that's kind of why we're really talking about this in a little bit more emphasis, because that's the thing. Okay, what about expected value? So what is the expected value of the weight of a potato? Well, in discrete land, we calculated the expected value as each value of x times the probability of x. But in continuous land, we can't do it that way, right? Because there are literally an infinite number of x values. And we can't say it's this value times the probability plus this, right? It doesn't work that way. Instead, what we're going to do is the expected value for a continuous random variable with a probability density function is going to be the integral of x times the probability of x on the interval. So this is the very general formula. If you're trying to find the expected value of x, it's going to be the integral of x times the function, the probability density function, over the entire interval. So in this particular example, it's going to be the integral from 0 to, sorry, not 0 to 4, 1 to 4. I keep wanting to start at 0 because it's typical. The integral from 1 to 4 of x times 3/14 times the square root of x. So we're just throwing in an extra x. Another word for this is a weighted average, right? When you're finding an average or an expected value, it is a weighted average, meaning, right, each value is getting multiplied by its probability. Each value x multiplied by its probability, 3/14 for x. So we're going to simplify this. X times x to the 1/2 is x to the 3/2. And then we're going to integrate. So the integral of x to the 3/2 is x to the 5/2 times 2/5. So we're going to get 3/14 times 2/5 times x to the 5/2 from 1 to 4. 3/14 times 2/5 is going to be 2 cancels. You get 3 over 35. I think, right? That looks right. Right? Cancel 2 here, 2 here. Yeah. And then we're going to plug in 4 and 1. So we're going to get 4 to the 5/2 minus 1 to the 5/2. 4 to the 5/2 is 32, minus 1 is 31. So you get 3 times 31, 93 over 35. Which, if you want to write it, so normally I wouldn't write this as a mixed fraction, but I will in this case. Or 2 and 23/35. So pretty close to like 2 2/3. Okay, it seems reasonable-ish that the expected value would be almost like close to 3 pounds. If you think about, if you look at how the distribution looks, right? The average being about there-ish seems reasonable. I should point out the average isn't where you'd have half the area on each side. That's actually what the median would be, which we'll talk about later. The average is kind of where things would balance. So if I were to draw a line cutting this along where the average is, these two sides should balance out, meaning like a teeter-totter, right? If you have things further away, if you have more stuff further away, that counts more than more stuff closer, because right, the length that you are away also matters when you're on a teeter-totter, not just the weight that's at the end. So I know my picture doesn't really do a good job of displaying it because it looks pretty compact, but it is the case that the average isn't where you have half the area on either side. It's where the whole thing would balance if you were to put it on a teeter-totter. Yeah, let's talk about the variance of this, which is going to be a little bit ugly, but it is worth calculating. So variance also has an analog. So in discrete land, variance was the sum from I equals 1 to n of x sub I minus the mean squared times the probability of x sub I. We're gonna have the same thing for an integral. For continuous land, our variance is going to be the integral from a to b of x minus the mean squared times the probability density function f of x. So this is not the best way to do it. Let me show you what I mean. So this is where instead of using this, there's an alternate formula. I'm going to show you the alternate formula just by actually doing the work real quick. So we're going to simplify this a little bit. So we're going to write this as the integral from a to b of, I'm going to multiply this out. X squared minus 2x mu plus mu squared times f of x. I want to make one observation. Mu, the mean, is a constant, right? We have found the mean. In our particular example, the mean was, what was it, 93/35, something crazy like that? Yeah. So just for later reference, right, our mean is 93/35. We'll plug that in later on. So now we're going to multiply this out. And look what happens. We get the integral from a to b of x squared times f of x minus the integral from a to b of 2x times the mean times f of x plus the integral from a to b of the mean squared times f of x. Okay, check this out. Constants can come out of the integral. There's no constant here, so that's just going to stay as is. What constants can I pull out of this integral? Right. So you get minus 2 mu times the integral from a to b of x times f of x dx. And then I can pull out mu squared here, integral from a to b of f of x dx. Okay, now we have to remember a couple things. If I integrate the function over the whole interval, what's that interval need to equal? Right. This is equal to 1 because we're just saying we're adding up all the probabilities, right? If we're looking at this, if we have our function f of x from a to b, one of the things that has to be true is that area has to be 1. The other thing that has to be true is it has to be a non-negative function, right? Your function has to be above the x-axis. Okay, and now let me ask you both, what's that there? The integral from a to b of x times f of x. Right, it's the mean. We just calculated it. So here's the alternate, easier formula for calculating variance. And I do strongly recommend using this formula we're about to write down. So not this formula here. This is the one way of writing variance. But the alternate is going to be the integral from a to b of x squared times f of x dx minus 2 times the mean plus the mean squared. So simplifying this, the alternate formula is that the variance is equal to the integral from a to b of x squared times f of x dx minus the mean squared. And that's going to be much nicer than doing your variable minus the mean quantity squared, multiplying it by f of x, and then integrating that. So now let's actually go back to our example. For our example, yes, we literally just showed that the formulas are actually the same, right? Because all I did was I started with this and I just manipulated it, right? I multiplied it out. I distributed the f of x to each term and broke it into 3 integrals. That one's just what it is. That one is, right, you're always going to get the integral from a to b of x times f of x here, which is the mean. And here you're always going to get the integral from a to b of f of x, which is just 1. So yeah, it's kind of cool, right? It always works out this way. So you can always, instead of using this usually messy formula, you can use this. In fact, let's write them both out to see how it looks. So calculating the variance here, the messy formula would give us the integral from 1 to 4 of x minus 93/35 squared times our 3/14 times the square root of x dx. That looks like it's going to be terrible, right? Because you're going to have to just multiply this out and then distribute the square root of x to each of those 3 terms. I'm going to have to do a lot of integrating, right? It's going to be messy. Versus the variance equal to the integral from 1 to 4 of x squared times 3/14 times the square root of x dx minus the mean squared. That's going to be a lot less work. It's still not going to be pretty, but doing this integral is way less terrible than doing that integral. So let's calculate it. I'm going to get, let's see, 3/14, the integral from 1 to 4 of x to the 5 halves dx minus, I'm just going to leave this as 93/35 squared. There's no point in trying to make it nicer. Integrate, you get 3/14 x to the 7 halves times 2/7 from 1 to 4 minus 93/35 squared. That's going to be, let's get cancel there. So you get 3/49 times 4 to the 7 halves is 2 to the 7th, which is 128 minus 1 minus 93/35 squared. So we end up getting 127 times 3, which is 300 and what's up to 3 is 81. 381/49. Seems wrong. Fine. Minus 93/35 squared. Which then I would just get a calculator and get approximately. Yeah, I calculate. Okay. Might not brought my calculator. I guess I'll use the phone calculator. You know how that's going to go. So let's see. So square that thing. I don't love phone calculator. So it seems like a good idea. It's always disappointing. I'm getting approximately 0.715. Yes. Oh, sure. So I multiply the x squared by the square root of x. What do we do with the powers when we multiply them together? Right, and 2 + 1/2 is 5 halves. So calculating the expected value and the variance of something like this can be a little messy. Oh, I suppose we should also talk about the standard deviation. So standard deviation is as easy as it ever was. You just have to calculate the variance, right? It's going to be the square root of your variance. So in this particular example, standard deviation is going to be approximately the square root of 0.715, which is approximately equal to come on, phone. Sure, fine. Be that way. Sorry. About 0.84. Okay. So these potatoes on average weigh about 2 2/3 pounds, and there's a variance of about 0.84 pounds. Okay, that doesn't seem totally unreasonable. More examples. Times. Oh yeah, we got that. So, as we were saying before, two things. Thing one, in order for f of x to be a probability density function, on the interval from a to b, two things have to be true. Thing one, f of x needs to be greater than or equal to 0 on the interval from a to b. And thing two, the integral from a to b of f of x must equal 1. Just like the discrete probabilities, right? All the probabilities have to be non-negative and they'll have to add up to 1. It's just here the adding up is finding the area of the curve. So with that in mind, let's look at the following problem. Given f of x equal to k over x squared on the interval 1 to 3 is a probability density function. Find k. Okay, so we need to show or determine that the integral from 1 to 3 of k over x squared, that better equal 1, right? We said it's a PDF. So now we have to figure out what the k value is going to be to make that true. So I would probably factor out the k, rewrite this as k times the integral from 1 to 3 of x to the negative second equal to 1. Some people like to divide by the integral, like say k is equal to 1 divided by the integral from 1 to 3. I feel like that's unnecessary. Let's just find the integral and then divide by whatever the number is. So we have k times, let's see, the integral of x to the negative second is x to the negative first over negative 1 from 1 to 3 equals 1. That's k times negative 1 over x from 1 to 3 equals 1. So that's k times negative 1/3 minus negative 1 is 1. Negative 1/3 plus 1 is 2/3. So I'm going to have that k times 2/3 equals 1. So that k is equal to 3/2. So my PDF is f of x equal to 3/2 over x squared, or preferably, I suppose, 3 over 2x squared. Now it's a PDF for sure, because the area under the curve is definitely going to have to be 1. This is a typical, like people ask this question all the time, like find the k value so that the thing you were talking about actually is a PDF. Let's find the expected value. And then we'll do one other thing, and then we'll call it a day, I think. Yeah. Expected value. All right, so our PDF is 3 over 2x squared on the interval from 1 to 3. So we're just going to calculate the integral from 1 to 3 of x times our PDF. Okay, so let's see, that's going to be, I'm going to cancel an x, so that's going to be the integral from 1 to 3. Let's factor out the 3/2 as well. 3/2 times the integral of 1 over x. So that's going to end up being 3/2 times the integral of 1 over x is the natural log of the absolute value of x from 1 to 3. It's going to be 3/2 times the natural log of 3 minus the natural log of 1. So you get 3/2 times the natural log of 3. Okay. Which, just because I want, there is a reason I want to know this, not just for fun. So natural log of 3, but come on, that's, I hate this calculator, it kills me. 10, 12, 4, 5. So that's a what's the problem, calculator? Okay, that's approximately 1.647. So graphically, 2, 3, we're about here, and our function looks like, well, so if I plug in 1, I get 3 halves. If I plug in 3, I get 3 over 18. I'm not sure, it's very small over here. So my function looks kind of like this. It's curving downward though. I didn't draw it very well, sorry. And so what we're saying here is right here, that's where the average is. Kind of interesting, right? It's very far to the left. Because this area over here and this area that's far out here, even though there's not as much of it, it's kind of counting from right. So again, I should say, if I were to like lay this flat area on a line that went through that point, it would balance like a teeter-totter, right? It wouldn't flip this way or that way. That's the average. Let's also talk about the median. So the median is the value that separates the lower half from the upper half. Often the median is a better measure of the middle in some cases, because sometimes you have really skewed data. The typical one you probably hear about is median household income. You talk about in the news, like the median household income is $40,000 a year or something like that. And the reason to talk about the median is because if you talk about the mean or the average, the people making gobs and gobs of money would really skew that data really, really higher than would be meaningful, right? If you, I don't know what the average income is because they don't ever talk about it, but it's probably something like, I don't know, I would make up something, but it would be wrong. I'll look it up and I'll find out. I do, and now I'm curious, like, what is the average income? It's probably much, much higher than the median. And so that data that doesn't really give good context to what people, most of the people in the world are really dealing with, right? These few people at the top are really skewing that data. So we said, well, let's not talk about the mean. Let's talk about the median instead, which is just, where's the halfway point? Where's the people halfway, half people are making less than that amount, half the, actually households, not people, half households making more. So when we want to find the median, what we're looking for instead of what we just found, 1, 3, right? So before our mean is about there. But now what we're looking for is the place where half the data, interesting. I expect that to be, I thought it was going to be bigger. We're looking for the place where half is below and half is above. So what we're going to do is we're going to say the integral from either 1 to m of your PDF should equal 1/2, or we can do the integral from m to 3. People most of the time, so right, we're looking for, and they happen to be very close to each other in this example. We're looking for the m value there, where to the left, there's half, and to the right, there's half. And it does happen to be a little smaller, actually, the mean here. We can calculate either one of these to get what m is going to be. Let's do this one. So the integral from 1 to m of 3/2 times x to the -2nd is going to be 3/2 times x to the -1st over -1 from 1 to m. I always want to rewrite this as -3 over 2x from 1 to m. And that's going to be -3 over 2m minus -3 over 2. And that should equal 1/2. And now we're going to solve for m. Yeah.
I was going to ask if we can put if 3/2 this function can be natural log of x, but we're not doing it.
Right. Exactly. Yeah. So let's see. Solving for this, I'm going to get -3 over 2m plus 3/2 equal to 1/2. I probably multiplied everything by 2m just to get rid of the denominator easily. Multiply everything by 2m, I'm going to get -3 plus 3m equal to m, and then 2m equal to positive 3. So m equal to positive 3/2. So 3/2, which is a little bit less than what our mean was. Our mean was like 1.6 something. 3/2 is the place where half the data is above and half the data is below. You would also have gotten the same thing if you had worked with this. If you'd set this one equal to 1/2, you would also end up getting m equal to 3/2. It's kind of neat. Yeah. That's it. That's all I got for today.